The sketch shown represents the end of a double-angle steel tension member with holes for a bolted connection. Yield strength of the steel is 50 ksi. Ultimate tensile strength is 65 ksi. The cross-sectional area of the two angles together is 2.88 inches squared. Holes are punched 13/16 diameter for 3/4 inch bolts. What is the design strength for block shear fracture? Let's go ahead and take a quick look in the FE Handbook on block shear fracture. And if you go to the FE Handbook, just type in the search bar tension members or block shear, and it should lead you to this page. Last few weeks, we have talked about the design yield or design strength for yield. We also have talked about design strength for rupture, and this is the formula for the design strength for block shear. And there are actually two formulas, and the final result is going to be the smaller amount. The phi for block shear is 0.75. UBS is 1 given to you. And there are a few other terms that we have to get familiar with. AGV is gross area for shear. ANV is net area for shear. And ANT is net area for tension. We're going to learn more about this once we solve our problem. Let's go back and do that. If you look here at this angle, if I have a force pulling in this direction, this connection can fail in this way. I'm going to draw a red line showing how this connection can fail. And when this connection fails in this way, this is called block shear failure. Where this plane shown in green, this is called the shear plane. Because when this plane fails, this fails due to shear. And in purple, this plane, this section here, it's called tension plane. So now let's talk about the shear plane and draw our shear plane, because we're going to have to calculate the areas. So if I look here and I was to do a section here, I'm going to get something that looks like this. And I have two of these because we have double angles. And I have a hole here and then another one here. And then at the end here, we have half of that hole. And we know the length of this section is this length over here. It's 8 inches. And now we have to figure out how much are all of these distances. How much is this hole over here? In the problem, we're given that the holes are punched 13/16, but that's not the dimension that we have here. And I've talked in the past, but I'm going to do it again. When you are given the bolt size, let's say this is the bolt diameter of the bolt. So when you're given diameter of the bolt, in order for you or for them to feed the bolt into the hole, we have to make the hole a little bit bigger, and that dimension is have to make the hole 1/16 of an inch bigger in order to fit the bolt. And in reality, when they do punch the hole, they actually damaged an area around that hole, which we cannot rely on its capacity. And that dimension around that hole, that area is another 1/16 of an inch. So the diameter is greater by another 1/16 of an inch. And this is the actual hole dimension or diameter that we have to take into consideration. So in the end, the actual hole diameter is equal to the diameter of the bolt plus 1/16 of an inch. And this is due to oversize. We have to make the hole bigger to fit the bolt. And another 1/16 of an inch. And this is due to damage that happens around that hole due to punching. So, and then when you are also given in the problem, holes are punched 13/16. When you're given in the problem the size of the hole, all you have to do is take the size of that, the diameter of that hole, which is diameter of the punched hole, and just add another 1/16 of an inch to it. Okay, so in our case, let's go ahead and calculate the diameter of our hole. And I will take the diameter of the bolt, which is 3/4, plus 1/16 of an inch, plus 1/16 of an inch. And this is going to equal to 12 plus 1 plus 1. I will get 14/16. And this will give me 0.875 inches. So my actual hole diameter that I have to take into consideration in my calculation is 0.875 one time here, and 0.875 another time here. And this is only half of that. So here I have 0.4375. And now we have to figure out these other dimensions. Since center to center, we have 3 based on what's shown here. That means that we have to subtract 0.75 out of 3 to get this dimension here. And this is going to be equal to 2.125 one time here, 2.125 here, and this dimension, center to the end, is 2, so we have to subtract half of this diameter to get this dimension here. And when you do that, you will get 1.5625. And now you can stop the video and just verify that all of these dimensions added together make 8 inches. And now that we have the shear plane, we can calculate the gross area for shear. And the gross area for shear is going to be 8 times the thickness of the plate, which is 1/4 of an inch, or the thickness of the angle, which is 1/4 of an inch. So I'm going to do 2 times 8 times 1/4. And this should give you 4 inches squared. We can also calculate the net area in shear. And the net area in shear, I will do it as gross area in shear minus the whole area in shear. Let's calculate the area of the holes. And this is going to be equal to, we have 0.875. Let's add all of this together, the length of that. We're going to have 0.875. We have 2 of these, plus 0.4375. And this we have to multiply it by 1/4. And we have to multiply this by 2 because we have 2 of these angles. And you should get 1.09375 inches squared. And of course, you can just work with 1.09. You don't have to carry all of these decimals after you. I'm just doing it because I have them. I don't mind. And now if we substitute in this formula, we have 4 minus 1.09375. And I get that the net area in shear is equal to 2.91 inches squared. So we have the both areas that we need for shear plane. Now we have to calculate tension plane, the net area for tension plane. And tension plane is going to look something like this. This is the tension plane. And we're going to have two of those because we have two angles. And I will have half of the diameter here. And now this dimension here, since the angle is a 3x3 angle, this is 125. So the total length is 125. And now we have to figure out how much is this. We know that this is half of the diameter, and half of the diameter, we have also already talked about it, is 0.4375, which means that this is 125 minus half of the diameter, and I get 0.8125. And now that we have this, let's go ahead and calculate the net area in tension. So the net area in tension is equal to 0.8125 multiplied by a quarter, the thickness. And I will multiply that by 2 because I have two angles. And you should get net area in tension equals to 0.41 inches squared. And here we go. We have all of the areas we need to go ahead and calculate the strength for block shear fracture. Let's scroll down a little bit. So the FE Handbook tells me that Rn is equal to the smaller or the minimum of 1 time Fu multiplied by 0.6 times net area in shear plus UBS times net area in tension. And the second formula is 0.6 multiplied by Fy multiplied by gross area in shear plus UBS multiplied by Fu multiplied by net area in tension. So what I will do, I'll calculate the first formula, and I'll call it Rn1 equals to, we know Fu equals to 65 ksi multiplied by 0.6 multiplied by A and V, net area in shear is 2.91 plus UBS is 1. It's given in the FE Handbook. Also, A and T, we have calculated it, is 0.41. You should get 140.14 kips. And now let's calculate Rn2, the second formula. Rn2 equals to 0.6 multiplied by Fy is given in the problem as 50 ksi. A, this is the gross area for shear. And gross area for shear is 4 inches squared plus UBS, which is 1, multiplied by Fu, which is 65, and multiplied by A and T, which is net area for tension. And if you go ahead and calculate all that, you should get that Rn2 is equal to 146.65 kips. Okay, so we have RN1, RN2, and you might be tempted to go look into the options. And here you might say, oh, C is 140, so C is the correct answer. But what I want to remind you is that these are the nominal strength for block shear. It's Rn. What the problem is asking us to calculate is the design strength for block shear. And in order to calculate the design strength, we have to multiply this by the phi factor for block shear, which we have talked about at the beginning of this video, and is given to you in the FE Handbook, that it is 0.75. So now we have to take Rn as a minimum of these two, which means that Rn equals to 140.14 kips, and that's the nominal strength, and the design strength is Crn equals to 0.75 multiplied by 140.14, and this is going to give you 105.1 kips. And this is your correct answer. Looking at the options, the correct one is A, 105 kips.